We are going to have a look at lemma 1.1, the integral form theorem. We have seen this actually in the last semester, so this is nothing new. Let's get to it. So, let omega be a subset of the n+1 dimensional real space, and let it be an open set. Now, let further f be a function mapping omega onto the real number line. And let it be a continuous function. And let x be a function. So this is very important. X is not a variable, it is a function. And it is a function of variable t. It will map some interval of the real line onto the n-dimensional real space. And let it be also a continuous function. X be a continuous function. And finally, let x be such a function, we have one more requirement, that its graph lies in omega. Then the following are equivalent. What do we mean by graph of x? Well, by that we simply mean an ordered y tuple, such that the first entry, or the first, say, a entries correspond to the input variables of x, and the remaining entries correspond to the individual outputs of x. Now, then the following are equivalent. Then, phi. 1. The ordered pair x, y solves the ordinary differential equation the ordinary differential equation x prime is equal to f of x of t with the initial condition of x of t0 being some x0. And this is equivalent to saying that x of t is defined as x0 plus the integral from t0 to t. Mind you, t is a variable here, so it's a integral with a variable upper bound of f of x of some variable s ds. So it's some integral function. And this is true for all t in I. So essentially, the ordered pair solves the differential equation if and only if it has this form with the given initial condition. Otherwise, there will be infinitely many solutions. Now, proof. Well, we shall prove that 1 implies 2. So, assuming 1 holds, assuming the first point holds, x is an element of C1 of I, meaning that x has continuous first derivative, first partial derivatives. This is continuously differentiable. Y, since x prime is equal to f of x of t, where f is continuous. This means that the integral from t0 to t of x prime of s ds is equal to x of t minus x of t0. What did we actually do? Well, we simply applied the integral operator function on both sides of this equality. Now, and as such, simply moving terms around, we get that x of t is equal to the integral from t0 to t of oh, pardon me, here of course there's supposed to be f of x of s. We get that x of t is equal to the integral operator with the input t of f of x of s and s ds plus the initial condition, which is precisely what we wanted, so that's okay. That's the first implication, and now we shall prove equivalence. So 2 implies 1. Well, we are assuming, well, what do we assume? We assume that x of t has this form. Has this form? Well, we definitely can differentiate both sides, since we assume the smoothness of everything, or at least continuity. Well, no, smoothness really, and therefore differentiability. So, differentiating the highlighted expression, we get that x prime is equal, the derivative of constant is 0, plus, and now we obtain the, we get simply that f of x of t and t. Why we have had a theorem for this in the last semester is a simple answer. It always works like this. When one has an integral operator of a single variable, and the variable determines the upper bound of the integral, then the derivative of this integral operator with respect to that variable gives us simply the integrand. And we also observe that x of t0 as defined is x0 plus the integral of t0 to t0 of f of x of s ds, which is x0 plus 0, which is x0. And this concludes this lemma.